we will see in detail. First, we will see what is normal Zeeman effect. Here, I have taken the hydrogen atom as an example because it's a simplest atom having only one electron. When a hydrogen atom is placed in an external uniform magnetic field, its energy levels get shifted. This energy shift is known as Zeeman effect. The Zeeman effect without spin of the electron is called normal Zeeman effect. That is very important. In normal Zeeman effect, the splitting of spectral line is determined by the angular orbital angular momentum alone. There is no role for the spin angular momentum. For normal Zeeman effect, uh, is concerned only about the orbital angular momentum, not the spin angular momentum. While in the case of anomalous Zeeman effect, it cannot be explained in terms of orbital angular momentum alone. We have to take care of the spin angular momentum also. In today's lecture, we will see both the cases. That is without considering the spin and with the spin under consideration. In the case of normal Zeeman effect, the spectral line appear as a single line when there is no magnetic field, and it will be split up into multiple line like what I have shown in the figure when you apply the magnetic field. Uh, Now we have taken an hydrogen atom as an example. Hydrogen atom principal quantum number value is 1. So it can take a L values. L is equal to, in the case of hydrogen atom, it will be 0. Start from 0, 1, it will go up to like it will go up to n minus 1. So uh, this is about the hydrogen atom. Yeah, when L equal to 1, so naturally it will take M value can take minus 1 to minus 1 to plus 1. Like this I have shown. It's minus 1 to plus 1. Minus 1, 0 is an integer value and plus 1. If L equal to 2, then you will have M will become minus 2 to plus 2, minus 2, minus 1, 0, plus 1, plus 2. So it will go like this. You can easily identify, you will have even, odd number of lines. When you apply magnetic field, you will get odd number of lines. Uh, so, and with here you can see the difference between on the one level and the another level is the energy difference is H cross multiplied by EB divided by 2ME. So here P is the applied magnetic field, M is the mass of the electron. So the energy difference is between the one level to another level is this much. Here, remember that in the case of hydrogen, we have triplet. So when L equal to 2, you have 5. So that is split into uh, odd number of line. So that is one important point. In the case of normal Zeeman effect, this is without considering the spin. We are going to see in detail about normal Zeeman effect. So this is without considering the spin of the electron. Just now we have seen in the case of hydrogen atom, when you apply the magnetic field, you will get a splitting up spectral line. So, and also we have seen this one, that is called EB by 2ME, that is called Lamar frequency. Lamar frequency. That is frequency due to up, the rotation of the electron due to the applied magnetic field. So This split is due to electrons orbital magnetic dipole moment. So this is due to orbital magnetic dipole moment. The magnetic dipole moment associated with the orbital motion is, by definition, it is equal to mu L is equal to minus over 2m L. Uh, L is the orbital angular momentum vector. So this is, see, normally we have to observe with three line or five line. That is, this is 2L plus one number of state. We will have 2L plus one number of state. So when L is the integer, then 2L plus 1 must be the odd integer. However, in the case of hydrogen atom, we are observing uh, even number of lines. How it is possible? Only when L is half integer, then you can have even number of spectral line. That is one interesting thing. We will see that. Just now I told that in the case of normal Zeeman effect, the split will be odd number, that is 2L plus 1. And also it is equally spaced. You might have noticed in my previous diagram, it is equally spaced with energy H cross omega L, where omega L is the normal angular frequency. So, if you got even number of spectral line, then there is some problem with it. Not a problem. If split is even number, that means we have to take care of the spin of the electron, that is which is a half integer. This disagreement is due to simplifying the assumption where the spin of the electron was ignored. Because in the case of normal Zeeman effect, we have ignored the spin of the electron. If you take care of the spin of the electron, then this will become uh, even number of lines. When L equal to half, then naturally this will become 1 plus 1, 2, like. So then this will be even number. So we can explain the result obtained experimentally. So far, we have seen the normal Zeeman effect, that is without considering the spin. Now we will see what will happen if we consider the spin. Already I have told that even number of spectral line split cannot be explained if we have ignored the spin. So you will get even number only if you consider the spin. Now we consider the spin of the atom is placed in the uh, uniform external magnetic field P external. The energy levels are shifted. For a single electron, the perturbation is H Z prime. This is perturbation due to Hamiltonian. In later stage, I am going to introduce perturbation due to fine fraction. So, which is equal to minus mu L plus mu S dot P external, that is applied magnetic field. Here, the mu L is associated with magnetic dipole moment due to orbital motion, and mu s is the dipole moment associated with electron spin. Here, mu l is equal to minus e over 2m into l, where l is the orbital angular momentum vector. Similarly, mu s is equal to minus e by m s, where s is the spin angular momentum associated with magnetic dipole momentum due to the electron spin. That is spin angular momentum. Here you can see that 2 is missing here. Here it is divided by 2. Here it is 2 is missing. So when you write this Hamiltonian, perturbed Hamiltonian due to Zeeman effect, here naturally here minus minus will get cancelled, so this will become E divided by 2m. Since here only m, so you are multiplying you are taking E by 2m as common, so naturally this will become L, and the second term will become 2s. The nature of Zeeman splitting depends critically on the strength of the external magnetic field in comparison with internal magnetic field that gives rise to spin orbital coupling. Now we will consider two cases. If applied external magnetic field is very much less than the internal magnetic field, then the fine structure dominates, and the perturbation due to Zeeman effect can be treated as a small perturbation. Now you consider the another case. The external potential magnetic field is very much greater than internal magnetic field. Then naturally the Zeeman effect dominates and fine structure become the perturbation. So either you can take Hamiltonian as perturbation or fine structure as perturbation. Depends on whether the external magnetic field dominate or the internal magnetic field dominate. So already we have seen now H prime, that is perturbation. The total perturbation is uh, sum of the Hamiltonian perturbation, sum of the Hamiltonian perturbation, this one. Hamiltonian perturbation plus the fine structure perturbation. So the total Hamiltonian is H is equal to H naught H prime plus H prime. H naught plus H prime. H prime we have seen H prime is equal to this one. Uh, HFS prime plus HZ prime. Here HFS prime is perturbation due to fine structure, and HZ prime is perturbation due to the Zeeman effect. Now we will see the strong field Zeeman effect. That is, the applied magnetic field is very much greater than the internal magnetic field. Then, as I said, the Zeeman effect will be dominates, and the fine structure become small perturbation. That is, the total Hamiltonian is equal to H naught, where H naught is unperturbed Hamiltonian. Then the second term is perturbed Hamiltonian due to fine structure. This is perturbed Hamiltonian due to Zeeman effect. Now we have assumed that external magnetic field is very much greater. So this third term will dominate. We can ignore this second one. That is fine structure perturbation. So the total perturbation is equal to H naught plus H prime Z. So already we have seen the perturbed Hamiltonian due to Zeeman effect is represented as E by 2m into Lz plus 2Sz multiplied with P external, that is applied magnetic field. Here you remember that since H commute with H naught, because H naught commute with Lz as well as Lz, they can be diagonalized by a common set of states, that is get vector, get N, L, ML, MS. Now we will see, as I said, we will see the strong field Zeeman effect. When the total Hamiltonian act on get NL, ML, MS, that is total Hamiltonian is written. I have shaded using highlighted using yellow color. H is equal to H naught plus E by 2m into Lz plus 2Sz dot P magnetic field multiplied with which act on this get vector. So when H naught act on this get vector, that is unperturbed Hamiltonian, you know very well this energy level, if there is no perturbation, energy level purely depends on the principal quantum number, that is inversely proportional to principal quantum number, the square of the principal quantum number. So this will be minus 13.6 electron volt divided by n squared. This is due to H naught. That you have to keep it in your mind. This is first term is due to this H naught. Then remaining thing perturbation. When this when the other term act on, when Lz act on this get vector, what you will get naturally when L act on Lz act on this get, you will get ML H cross. You know very well. We have seen this in the when we are dealing with orbital addition of angular momentum. So this is ML H cross. Already there is 2 divided by sorry E divided by 2m. So here ML H cross. What will happen when 2Hz act on this gate? You will get sorry, you will get 2 ms, 2 times the ms. When sz act on ms, you will get ms, 2 ms, because this is 2Hz. Of course you will get one H cross. So I have taken EH cross over 2m as a common factor, then this will become ML plus 2ms plus the external magnetic field. Here you can see, uh, 1 minute. Here you can see this this EH cross over 2m. This EH cross over 2m is mu p. Where this mu p is called 4 magnetron. Then as usual, remaining time will be as it is ml plus 2ms into, of course, you have p external, that is the external magnetic field. Uh, these terms which I have shown in the rectangular blue color box is called Paschen-Back shift. This is Paschen-Back shift. This is for a strong field Zeeman effect. Now we will see about the weak field Zeeman effect. Uh, as I said already, in the case of weak field Zeeman effect, the internal magnetic field is very much greater than the external field. So naturally, the fine structure dominate, and the Hamiltonian, perturbed Hamiltonian for Zeeman effect can be treated as a small perturbation. As usual, the total Hamiltonian can be written as H naught plus HFS prime plus HZ prime. So you know very well that Hz prime is equal to e power, sorry, e divided by 2m Lz plus 2Hz. Now what I have done it here is, of course there is a dot product with the magnetic field, external magnetic field. What I have done here is, I have separated 2s z as s plus z plus s plus z. Now you can see this L plus z equal to j z. This first two terms, L plus z, L plus z is equal to jz. Then sz is there. Of course, that P external magnetic field will be there. So there is an external magnetic field. Since HF prime, HFS prime is a dominant perturbation, the best eigenstate to use are the get NLJ. Remember that earlier we have used ML. Here we are using J and MJ. In presence of spin orbit coupling, L and S are not separately conserved. Is conserved. L and S are not separately conserved. That is a very important point to be noted. We will see what will happen to this. So now the total Hamiltonian can be written as H naught unperturbed Hamiltonian and perturbed Hamiltonian of fine structure, and this third term is perturbed Hamiltonian due to Zeeman effect. In first order perturbation calculation, the contribution of the perturbed Hamiltonian due to Zeeman effect can be written as EZ1, that is one represent first order correction, Z represents Zeeman effect. So it's equal to the expectation value like NLJMJ e power sorry e divided by 2m jz plus hz dot p get NLJMJ. Here you can separate this in terms of two operators. Others are constant. So you can take 2 em, 2 by em, sorry, e by 2m and p external outside. So the first get operation is with respect to jz, and here also I have taken e divided by 2m pz as a common, and we are going to carry out the uh, operation on this get vector using sz. First, what you will get when jz act on this get vector? Uh, you will get mj h cross, mj h cross. So here one h cross term comes, and of course you have p external. That is the external magnetic field. Second term, right now I am keeping as it is. We will see what will happen to this second term, because we have to the get will the SZ operator SZ act on this get, which is somewhat complicated. We will see what will happen to this. Now we will see about second term. As I said, when HZ operate on this get vector, the result will be somewhat complicated. It's a tedious process, but I have written the answer straight away, uh, and I have shown it in the yellow color highlight. So when NZ act on this get vector, we will get H cross J into J plus 1 minus L into L plus 1 plus S into S plus 1 divided by 2J into J plus 1. Of course, here MJ will come, here one H cross. Now what I am going to do is I am taking this factor as it is common to both. That is EH cross over 2m mj p the magnetic external magnetic field p external. So here in the second term also this one is common. That is this is common for second term also. See, in the second term, you have E H cross 2m, E H cross divided by 2m, and of course mj E external. So I have taken this out. Remaining term I am keeping inside the bracket. that remaining terms which I have shown in the uh, green color bond uh, is called GI, Landau factor. Landau factor. This is Landau splitting factor. This one comes because this first term, 1 plus this thing is called GJL, Landau factor, uh, which is the critical parameter in the fine structure splitting. So this can be written as one more important point is see here uh, here this term. Oh, 1 minute. I'll erase this one. This EH by 2m, EH by 2m is 4 magnetron. This mu p. Of course, here you have mj, uh, then external, and this G factor. So the first order energy character due to Zeeman effect is equal to mu p mj, the external magnetic field, into Gj, that is a lambda factor. Thank you very much for watching my videos and supporting me continuously. Kindly subscribe my channel. My channel ID is youtube.com/@vasuv physics. Thank you very much.